Hello?
Bueno.
Hello?
Bueno.
So, I'm sorry. I apologize. I'm not allowed to joke anymore. I need to be serious about the math.
Yes.
True.
So real math, like Mother Russia.
Okay,
All right.
let's go.
Okay, so inflection point. So now suppose a function is differentiable on an open interval, remember, parentheses, open, containing c, that means c is somewhere in between there. Then the concavity changes at the point c and then f of c. F of c.
Oh, wait.
F of c. What is f of c?
So it's like just that one which we find from the second derivative?
It's the x. Okay, this is going to be the x from the second derivative, right?
Yeah.
And what is this piece going to be?
We plug in x.
You plug in x to where?
Why? That's what that function.
Secondary is
No, it's just
The function. You plug it into the function, the original function, right? That's what we have to get. So the x from that is going to tell me that, oh, hey, this is the point that is going to change. So my x value I'm getting from my second derivative, I plug that into my original function, and that's going to give me the point in which it changes inflection. Okay, that's where it's changing concavity. Condition for inflection point. Let f denote a function that is differentiable on an open interval a to b containing c, and the point c, f of c is the inflection point of f, then either f double prime of c is equal to 0, or it does not exist at c. So it's possible that I could take a derivative of the function, but it's also not going to exist. We did a couple of these problems the other day where my derivative did not exist, right? If my derivative does not exist, that's also going to be one of the points. So it's either going to equal 0 or it does not exist. Remember, when I have like radicals, like the square root of x, when I take the derivative of that, it actually goes down in powers, which is going to give me a radical in the denominator, where I cannot have zeros in the denominator. Okay, so let's see. Here's the steps. Find all numbers in the domain which the second derivative is equal to 0 or does not exist. Step 2, use test of concavity to determine concavity of both of f on both sides of each of these numbers. If the concavity changes, there's an inflection point there. Otherwise, there is no inflection point. Does that make sense?
Yeah.
That third one. If it doesn't go from positive to negative at that point, that means that there is not going to be a change in concavity.
My goodness, new students.
I know, great day, new student.
Wow, we
Oh my god, this class is overfilled.
Okay, wait, I'm sorry. I'm not allowed to joke during this. I can't joke. The math is serious.
Yeah, but I'm not gonna watch this one. So
I
you can joke right now.
can joke right now. Thank you. Okay, good. Is good. All right.
Let's go.
All right. So if it doesn't change from positive to negative at that point, then it means that there is no inflection at that point. Okay? There's going to be no inflection at that point. Don't look at that. There we go. Spoilers.
I took a picture.
Okay. All right.
That's pretty.
So you ready?
No.
Yes,
Find the
go,
inflection
go.
points of that.
Okay, go.
So let's start with the first derivative. So f prime of x is equal to
5 over 3x.
5 over 3x to the
2 over
2/3. Remember, it's a fraction, I'm subtracting 1. In that fraction, I'm subtracting 3 over 3, right?
Yes.
Yes.
Yeah. Let's
Good. All right. Is good. All right. So f double prime of x is equal to
10 over 6 to the x to the negative
10 over what?
6.
10 over what?
Oh, 9.
Nine.
Sorry.
Thank you.
Minus
10 over 9 x to the
negative 1 over 3.
negative 1 over 3 because I'm subtracting 3 over 3 again.
Oh, that's 3.
Yeah.
I know.
Okay, so now let's take a look here. So given this much information I have,
Equals to 0.
set it equal to 0. So 0 equals, now I'm going to rewrite this so I don't have the negative exponent. So I'm going to rewrite it. So now it's going to be 10 on top
10 over 9.
over 9 x to the positive 1/3. So if I bring this exponent down to the denominator, it changes from a negative to a positive, right?
Is that 2 over 3? That's 3 over
Why?
3.
Because if
The
it's
first
equal to
one.
0, then
5 over 3.
Just accept.
Are you talking about this?
No, the other one, the
no,
exponent
don't
and
work on
the
it.
exponent.
Yes, that's 2 over 3, yes.
You said that's 3 over 3.
No, you're subtracting 3 over 3. Because it's 5 over 3 minus 3 over 3. Because 3 divided by 3 is 1, right? Yes?
Yeah.
Because you're subtracting 1 from the exponent, that's how I get 2 over 3.
So they thought of it and did it.
I'm sorry.
That does not exist.
I'm sorry. You know what? I apologize. You know what? My handwriting is not that good. The more that you actually come to class, you could actually see, make out my poor handwriting.
Yeah, exactly.
Okay, so right here, equal to 0.
Yes.
Is there any place in which that this cannot be defined?
Everywhere.
Everywhere.
Nope.
Why?
It's undefined.
It does not exist.
Because
Where?
Everywhere.
Everywhere?
Yeah, because the bottom should be equal to 0
Not true.
if
Look at the function.
To get 0, the x has to be equal to 0.
yeah,
Wait,
but
isn't
we
it
can
gonna be-
subtract on 0, so it does not
That's what we're talking about. Okay. Is there a place, remember we're checking right here, F double prime does not exist. Is there a place that F double prime does not exist?
Yes.
Where?
X not equal 0.
X equals 0, right?
Not equal 0. Right.
At X equals 0. The reason why I'm saying that is is it differentiable? Yes. I can take the derivative. Can I plug in 0 into my first derivative?
Yeah.
Yes.
Yes. Can I plug in 0 into my function?
Yes.
Say yes.
Yes.
Yeah.
So it is allowed for my function and it is allowed to my first derivative, right? Yes. So since those are allowed, this is a place in which that only the second derivative is not going to be there. Okay, so it's going to be undefined only for there. So this is going to be the point in which I'm testing this for concavity. Because if I go back to my checklist again, so it's double prime equal to 0 or at which that del prime does not exist. Right here we got del prime equal, right here, right? Okay, so let's check numbers here. So on a number line, I have 0. Check -1. Check -1. So I plug in -1. Am I allowed to put a -1 into a third root? Yes. I'm not allowed to put it in an even root, right? I can't put a negative into a square root or a fourth root or any of those, right? The even number roots, that would give me imaginary numbers. It would give me i's. But I'm allowed in a third root. Because -1 times -1 times -1. So that's the third root, right? So that would still give me -1. So it is allowed right here. So now that means that -1. So this would, if I plug it in, I get -1, right? So I get negative 10 over 9, right? Yes? So this over here is going to be negative.
Can you say that again? Or like the number line?
Okay, watch this, watch. Okay, so this is my f double prime not equal to 0, or f double prime does not exist, right? Okay, so that's where I get from this here. And now it's going to be 10 times 9 -1 to the 1/3. Yes? -1 to the 1/3 power is going to give me -1. Okay, if you question it, go ahead, put it in your calculator. I know you don't have your calculator right there because I can see your calculator right there. Yeah, so put the phone away, please. Thank you. Okay, so all this is going to be negative. All that's going to be negative. Now let's check the other side of it.
Positive.
let's check positive 1.
Which positive?
So the whole thing would be 10 over 9. This is positive. So let's go back. So going from negative to positive, if the concavity of F changes at the point, then this point is an inflection point. Is it changing negative positive or positive negative?
Yeah.
Yes, it is. That is going to be a point of inflection on this. That means that the left-hand side is negative, so that's good, should be concave down, and the right-hand side of this should be concave. Let's take a look.
So it's kind of like an is, but not
Let's see. So it is x to the 5/3, right?
G.
X caret 5 over 3. There we go. So right here, let's look. All this is going to be concave down, right? And the right is concave up. So negative, concave down, so this would be, okay, sum to this. And so since my second derivative, I only get 0. So the slope is equal to 0. So it's not going to have a min or max. Okay. So if I'm looking at my first derivative, it's going to be a positive, positive, positive to 0. And then on the right-hand side, it's also positive, isn't it? So looking at my graph, I have a positive slope to 0 right here, right? And on the right-hand side of 0, it's positive slope again, isn't it? So this right here, it's not going to be a min or max, is it? Because there's no change in this. It's not changing from a positive slope to a negative or a negative slope to a positive. So there is no change in that one right there.
So there just won't be anything.
Yeah, so right there, that's just going to be the changing concavity. All right, so let's see. Make sense? Okay, so this is going to be inflection point. So now my point is going to be 0, right? So it's 0, comma. Now, what did I say to do with that 0?
Put it in f of x.
Put it into f of x. So if I put it into f of x, this is going to give me 0. So my point of inflection is going to be 0, 0. Is good. Don't look at that. Okay. All right, the graphs of f and f double prime are shown. Assume f is continuous for all real numbers. Okay, so now if this is f, what does f actually tell me? Slopes, right? Okay, so now every place that the slope is equal to 0, what does that tell me? It's going to be a min or a max, right? Min or a max. So now I have this, and I have this. Okay, you'll see on this one. So let's talk about the first derivative first. So you can't think of it as a regular function graph. These numbers from here to here are what types of numbers? Positive, very good. They're positive numbers, right? So that means that right there, that's all positive slope, right?
Yeah.
Okay. I'm going to change color on this one. And all this right here is, those are negatives, right? So what did I just show? Right there at 0, right there at 0, what did I show?
There's a change.
There's a change, right?
Yeah.
So if it's a change from a positive slope to a negative slope, that means that is a
Minimum.
remember positive, think about slopes. Positive numbers, right? So you can't think of it in terms of this is my function. Okay? Just think about. So if I have a slope going up, 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 up to a point, then all of a sudden it's going down, down, down. So it's negative going down. That's going to be a max. So you can't think of it in regular function terms.
Basically, don't be looking at the graph.
Yeah, so you're just finding zeros, right? So everything up here, everything over here on the left-hand side is all positive numbers. So if those are all positive numbers, that means it's going positive slope to negative slope. So there is a local max at, zeros. It's not 0, 0, it's just 0. Because I don't know what the function is. Okay, so local max at x equals 0. Okay, good. Now over here at 4/3 comma 0, my slope, all this in green is all what?
Negative.
Negative. Okay, so just think about the where this is located at. This is all negative stuff down here, right? And at this point, it is now on the other side is all going to be positive numbers. So if it's going from a negative to a positive, think about the slopes. Okay, you have to imagine it, okay? So it's going to be negative, 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 down to 0. And then now all of a sudden at that 0, it starts going positive. So if it's changing from a negative to a positive, that's going to be a what? That's a local min. At x equals 4/3. Not bad, right? Does that help you? Or did I confuse you? Just let you know, when I was taking calculus, this is probably the biggest issue. I could not get my mind wrapped around the fact that this is not a graph of the function. These are to tell me it's a graph of the slopes.
Oh.
Okay? So when it's way up here, let's say right here. So right here, the slope is 2. At that point, the slope is 2. At this point right here, the slope is 1. So it's a positive 2, and then it's a positive 1, and then right here, the slope is 0. So it took me a long time to finally grasp that. And I understand it is just difficult because you've always been looking at just regular functions, not functions of the function. Yeah, anyway, all right. So here's the second derivative. What does second derivative tell me? Concavity, right? All right, so now, when this is going to be 0, when these are 0, that's going to be the change in concavity, right? Okay, so think about the numbers now. In a change in concavity, right here, all of this right here is all negative, right? Okay, what happens if it's negative?
It's going to be a concave down.
Concave down, right?
Yeah.
Negative is going to be a concave down. So I have everything on the left-hand side of this. Those are all negative numbers, right? So that means that all these numbers are concave down, right?
Yeah.
It goes to 0 right here, right?
Yeah.
So from here, let me change colors, to right here. Okay, so right here, on the right-hand side of this point right here, what are those numbers?
Positive.
No, look.
Negative.
These are still negative, right?
Oh.
So if you think about it, I have negative concavity on the left-hand side, and I have negative concavity on the right-hand side. Is that going to be a change in concavity? No. Because to be a change, it's got to go from a negative to a positive or a positive to a negative, right?
And so then like half or like
So right here, this is
the
just,
green one?
it's not going to be a point of inflection. It's not going to be a point of inflection. Make sense?
Yeah.
Yeah.
Because I have to. But now over here, at 1, it's going from, so on the left of 1, it's negative, isn't it?
Mhm.
And on the right of 1, it is Positive. It's going from a negative to a positive. So that means that the left-hand side of 1 is going to be concave. Left-hand side, the green part. So negatives, remember? A negative is going to be what? Down, right? Negative is going to be concave down. Okay, negative is concave down. And the positive is going to be concave up. So it's changing concavity right here. So an inflection point changes concavity. So this right here, this point, is going to be my inflection point. So this one actually does have one here. This one right here does not. So a point of inflection would be x equals 1.
But we only look at
Why is there not one here? Because it's negative and negative on both sides. What's up?
only when it's at 0, right?
Yes. When it's equal to 0, that's going to be the inflection point. And you have to test it to see. So we looked at this one. So if I did a number line, right here and I said, hey, look, we have 0, this is negative, and this is also negative. So if there's no change on either side, that's not going to be an inflection point. Okay? Make sense? Good. Oh, all right. We already found all those. Okay, so now, second derivative test to find the local extrema. So what this means is, when I take my first derivative, okay? I take my first derivative and I get my values, right? I set that equals 0. Yes? Okay, so it's basically f prime of x equals 0. And I find my points, right? And then we're checking for concavity at those points. If it's positive, if I take, let's say x is the c value here, right? If I plug that number, it's a positive. Positive is concave up. Remember? Like this with your finger. So it's positive is concave up. And that means down there, that's going to be a minimum. Okay? This is going to be a min at that point. The other way around. So if it's negative, got my finger there, right? Negative. So the point for my first derivative, so plug it in there. That's going to be my maximum. Okay, it's concave down. That's going to be my maximum right there. And I guarantee you I'm going to drill this into you. And I know it's going to work because while you guys are taking the test, I'm going to see that. You guys are going to do the hands. Be throwing up gang signs at everything.
Is it a positive?
Okay, it wasn't that funny. All right. Okay. Anyway.
I can just imagine we were doing that.
Yes. No, seriously, I see it. Every year I see the same thing. You know, during the test, they're like, and they're fitting it together. So they're like this, and then the type of function, yeah. So, and the AP exam, you can tell what questions they're on too. So when it proctoring the AP exam, it looks like that. They're like, and yeah, because other people that are not math teachers actually give the exam. So it's like counselors and stuff. They're like, what are they doing? They're like throwing up gang signs. Okay. All right. So makes sense. This is what we were talking about. Okay. Local max, local min.
Oh, spoilers.
Spoilers.
So you're gonna say this whole
We can't do that. Let's not do it. We don't have time.
All right. Hold on. Let me see. How many slides do we have left? Oh. I wasn't gonna do this one. Yeah, don't worry about this one here, but crap, I am out of time. Dang it.
That's fine.
Okay. So yes, I'll do this tomorrow, but tomorrow's going to be a homework day. All Wednesdays are supposed to be homework days from this point. Okay, so we will finish this one tomorrow.
Do we need